Okay, in this quick video, I'm going to walk you guys through everything that you need for this upcoming project. All right, so here's our page, right, under the Unit 3 assignment that describes everything you need to do. I would imagine the first thing you're going to want to do is go and pick a data set. Okay, so if we go to Content and then to Course Resources, then you scroll down to the very bottom. We've got the SPS discussion data files, right? And then pick one of these and download it to your computer, right? I'm going to take garbage and I'm going to download this just because I don't think anybody's going to pick garbage, and I don't want anybody to do the one that I'm going to do. So I'm going to save that to where I know where it is on my desktop. Okay, now you want to let's go back to the page we were at so we know what the instructions are, right? So back to Unit 3, back to the assignment, scroll up, our Unit 3 assignment, just so we have the instructions back here. Okay, so make sure you know where you saved it. For me, it was on my desktop. So launch SPSS, tell it to open another file if you have something open before. So if I double click on that or click and then hit open, it brings up a little box that says, okay, what do you want me to open? Now you got to go find that file. So for me, it was on my desktop. Double click on that. An update is available. Sure, I can do that later. Not now. Okay, this is just the output window that's just telling you it downloaded your file. You can minimize that. You can probably even close it. Here's all of our data. You'll notice that this set of data has all ratio level, or what they call scale. You see how it says measure scale? That's what SPSS member calls ratio level data. So all of these variables can be used to compute any kind of statistics that we need to compute. Okay, I'm going to pick two that I would, or one, depending on the questions they want us to do, that I don't want you guys to pick, right? So these are now going to be um, off limits. Cannot use other, and then let's see if we need to. But in any case, let's go through the questions. So the first one, given a different, given different sets of data, the student will classify variables within the data set by the level of measurement and whether the variable is continuous or discrete. Okay, well, the other data set, we really have no idea what that is, so it's kind of hard to figure out in context whether or not it is continuous or discrete. But since we see all those decimal places, I'm going to guess that it's most likely continuous. Decimal places is a telltale sign that you have continuous data because that's something that's being measured, and because we can measure it to more levels of accuracy, and therefore we're going to get decimal places. Discrete data is almost always going to be just whole numbers, right? Integers. So we would say, okay, this is a scale level, right, or ratio level, and it's continuous. So that's question one. Done. Easy. Simple. Okay, given different variables, the student will select the appropriate graph to display the variable and will use SPSS to create the graph with all appropriate labeling. All right, well, because we have continuous data, and because we have ratio level continuous data, the type of graph we would use for this would be a histogram, right? If you had discrete level data, you would want to use a bar chart, which is kind of usually what it defaults to. You could also use a pie chart if you wanted to be cute, because those are just for categories. So if you had nominal level or ordinal level data, you could use a pi for those. If you had nominal or ordinal level data, you could also use a bar, because again, these are just categories, right? So nominal would be categories, and then ordinal is pretty much the same thing. It's just categories with an order to them. So you would use those two for those types, and then whenever you have scale, you'd want to do a histogram if they're continuous. And then if you have scale discrete, so for instance, if we were going to use something that looked like it had nothing but whole numbers, then we would still want to go back to a bar for those, right? So scale continuous, the best thing to use is going to be a histogram. So I'm going to choose histogram, right? Drag it up here. Then I have to put in what my x-axis is. And remember, we're going to use the other, right? So weight of other discarded things goes here. And then try and, try and have some fun with it. You can display the normal curve on it. You can play around with the chart appearance. Maybe change some colors. Maybe you like green or yeah. And then you can, um, I believe there are ways to put a name on it. I guess it already does it for you, but you can customize that, right? You can click on here and you can customize that. But that should probably be enough. And then just say OK, and lo and behold, here is my histogram. Terrible looking histogram, right? No, it's fine, but it's obviously skewed to the right. It's a severe skew. Um, we can tell it's a severe skew because of this big tail. This is my mean. If I calculated the median, then I could see even better how the two, are hugely different. Double click to activate, right? And so it kind of puts it in your own window, and then you can play around with it. You can change it up and do all sorts of options to it, and make it pretty and play with it. Then if you want to put it in your Word document, it should be pretty easy. You can just copy chart, open up Word, and paste. And there it is, right in my Word document. Okay, so that would be that part. We'll go back to the next one. Given different variables, we'll select the appropriate numerical descriptive measures to describe the central tendency and variability of the variables, and we'll use SPSS to create the appropriate numerical output. All right, so back to SPSS, and this is our output, right? So we can get rid of that again, or just get it out of our way. Go back up to the main screen, and we want to analyze it. And remember, we do descriptive frequencies gives us all the stuff we want. So again, I have to choose the other variable because that's the one we're doing. I'm going to click on statistics because I want to designate what I want to run. So I'm going to do mean, median, and mode because those are the biggies. Let's go ahead and do skewness so we know how skewed it is. Let's do standard deviation. Why not? Minimum and maximum. Quartiles, well, let's do quartiles too, just so we can talk about all of them. Okay, continue. Okay. And then here are my outputs. Okay, so there's my mean, there's my median, there's my standard deviation. So you can see that the mean is substantially bigger than the median, but not really substantially in terms of a standard deviation, right? That is 2 points. Let's say these are points. These are probably, I don't know, measurements in tons or something because it's weights, right? So let's just say it's 2 tons. That's 2 tons bigger. But our standard deviation is 4.5 tons. So the mean is being pulled to the right. It's bigger than the median. So we know that it's skewed to the right, but we already knew that from the shape of the histogram. But it's not, even though the histogram looked fairly severely skewed, our skewness is only a little bit bigger than 2. And the rule of thumb is usually Anything bigger than 2 or smaller than -2 is what you consider to kind of be skewed enough to warrant, other measures. But this is just barely bigger than 2. And there are other measures out there you guys can research. They're really simple ones where you take the standard error. I think you take skewness and divide it by the standard error, and that gives you something that's similar to like a z-score. And then there are tables, and they tell you, hey, if it's above this, then you consider it skewed and blah, 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 blah. Do some research. Just do a quick little Google search on skewness and you'll learn something new. But for the most part, you can really just look at these three numbers and go, all right, it's two points bigger. A standard deviation is, sorry, let me get that out of the way. A standard deviation is 4.5. So this is like half of a standard deviation away. That's not too severely skewed in my book. So I would say the best thing to report for this would still be the mean, but I would report the median as well, just so the reader could see that there is a difference, right? So those are that's probably the best measure of center. The median would be, a secondary choice. A mode is no good at all. Modes we only use for measure of center for frequency counts, for, remember, qualitative data, things that's usually the nominal level or ordinal level. Standard deviation would be our best measure of spread. And then we could report percentiles, which is another version of spread. So usually what happens if our data is not severely skewed, we use the mean and the standard deviation. If the data is severely skewed, we use the median and then the quartiles for spread, right? So the median for center and quartiles for spread. If it's not skewed, we use the mean for measure of center and the standard deviation for measure of spread. So those are kind of the rules of thumb. And then, every researcher kind of decides for themselves whether or not it's skewed enough to forego using the mean and the standard deviation and instead report the median and the quartiles. You'll notice that the 50th quartile is the same thing as the median because that's what it is. It's at the 50th percentile, right? It's right in the middle. So this is Q1 and Q3. 25% is the first quartile, 75% is the third quartile, right? Quarters, quartiles. And that's it. So this distance between these two quartiles, if you did 3.7 minus the 0.23, so basically 3.5. 3.5 is what's called the IQR, the interquartile range. And that's just the distance between your quartiles. And that's usually the measure of the measure of spread that is reported when we're using the median. Okay, so you could talk about, either or both or whatever in your paper, but that's all that stuff that you would need for that part. Okay, what else? Given two variables, so we'll determine if there's a linear relationship between those variables using the Pearson correlation coefficient, and we'll create a scatter plot of the two variables. All right, so that's something we didn't have a chance, we didn't have time to do last time, so let's do that now. Okay, so let's do the scatter plot and the linear regression stuff. What I'm going to do, and I'm no expert at SPSS, but I think probably the easiest way to tackle this question is just go run a scatter plot. So go to Chart Builder, and I've already set it up where I chose other was my dependent, or sorry, my independent, and then total is going to be my dependent. Please listen to me very carefully. Do not use these two variables. In fact, do not use total with any of these because total is absolutely dependent on these things because it's created by adding all these things together. So you're going to get a stupid who cares result. Instead, just pick. So remember, I don't want anybody to use the other variable in garbage. In fact, I'd rather if nobody even uses the garbage data set because I've done this video. But if you want to use garbage, just don't use other and don't use other in total. And in fact, don't use total at all. If you use any other data set and it's something similar to this where it has a total column, please do not use total as your vertical, as your y, as your dependent variable, because it's going to give you a relationship because it's a no-duh relationship. Instead, use two others because the whole point of this is to figure out, do these things have any kind of relationship? So you'll just get more interesting results if you do it that way. Okay, so just like before, you want to choose this one because it gives you a fitted line. So you drag this one up right here, and that's how I got that, right? And then you drag your variables down here. So I drag that one there, and I drag the total over here. And that's really all you need to do. Just hit OK, and it's going to create this nice little scatter plot for you. So just like before, you can double click to activate it. Then you can go up here and do edit, right? Copy chart, and then go into your Word document, put your cursor wherever you want, Control V, and paste it. Okay, so you've got your scatter plot. You'll also notice up here in the corner, you've got r squared linear equals 0.389. So that's your r squared value. It's not r, it's r squared. But I think they tell us that they want us to, where is it? Two variables, determine if there is a linear relationship between those variables using the Pearson correlation coefficient. Well, using the Pearson correlation coefficient means R. That's what Pearson correlation coefficient is R. So if we have R squared, all you have to do is take out your handy dandy calculators and take the square root of that number, and that's R. I mean, it's literally that easy. I mean, R squared does in fact just equal R being squared, right? All right, so I'm going to break out my calculator, and I'm going to calculate the square root of 0.389, and it gives me 0.623. So I'm just going to type it up here. So my R, right, is going to equal the square root of 0.389, which equals 0.62, let's say 37 if I go to 4 decimals. Now, okay, great. So I've got an R of 0.6237. What the heck does that mean? I can look at this graph and I can tell you they really don't have a linear relationship. You see how there's this big blob that kind of goes vertically? This line doesn't fit very well. So I'd say there's not really a strong linear correlation. And in fact, 0.623 is a pretty weak R. Your R ranges from -1 to +1. +1 means you have a perfect linear relationship and the line would have a positive slope, and a -1 would mean you'd have a perfect linear relationship and the line would have a negative slope, right? It would slope backwards. Anything close to 0 means no relationship at all. 0.6, that's almost halfway in between 0 and 1, so it's got some relationship, but not a lot. There are actually charts, tables online that tell you whether or not we would consider this a significant result. And it's all based on how big your sample size is. So the first thing you have to do is figure out how big your sample size is. So if you scroll down to the bottom, you can see I have 62 pieces of data, right? The last piece of data ends on the 62nd line and it starts on the first. So my sample size, N, is 62. All right, so let's not do that because then it goes away. N equals 62. So what you can do is you go online very simply and search for Pearson correlation coefficient table. And it'll give you a bunch of different things. Table of critical values, Pearson correlation. That's pretty much what I want. So let's click on that and see what we get. Yep, and this is exactly what I need. So it's table of critical values for your Pearson correlation. All right, we normally want to test things at the 0.05 level. So this is what you would choose, and this is what you would talk about in your paper, that you're going to set alpha to equal 0.05. That means you're looking for a 5% error. So now we go down to our sample size. Remember, our sample size was 61, right? I think it was. Yeah, 62. So we go to 60 because you basically go to the biggest number that's still less than it. And then you go over to this column, which is where the 0.05 was, and it's 0.250. What that means is, and this is if we're doing a two-tailed test, we're just looking for something that's different. If we were doing a one-tailed test, we'd be over here. don't worry about it. We haven't discussed this stuff yet. But for the most part, if you really want to be cool with your paper, you would look at a table like this and go, well, technically, with a sample size of 60, our Pearson correlation coefficient only has to be greater than 0.250 for us to say that we do in fact have a significant relationship. Because the sample size is so large, you can see these numbers go down as the sample size gets larger. If you can see a relationship with only a few numbers, that doesn't mean a lot. So that's why small samples need really big numbers, right? Really close to 1. But as your sample gets bigger, then the smallest kind of relationship ends up being significant. So technically, we would say that these numbers these two sets of data do have a significant linear correlation because our Pearson correlation coefficient, or R, was bigger than 0.250. But that being said, it's still a pretty weak one at 0.6. All right, and that would be everything you would need to answer that one. Then, given output generated, the student will provide the correct interpretation of the output, including rationale for that interpretation. Well, we've basically done that with all of our outputs, right? So you're just providing all those graphs and interpreting all of them and discussing how they relate to what we're discussing. Okay, so that should be it, guys. That should help you do everything you need for Unit 3. Um, Maybe I'll see you in seminar tonight or Sunday. Remember, if you don't show up, no biggie. Just submit a couple sentences, explaining this video or any of the other two. Like, you can use this as the one that you're going to describe, and that's good enough for your attendance.